Hi, well, welcome to today's lesson. We're going to talk about exponential functions today. And the first thing you want to do is put your notes down in your notebook, document those page numbers in your table of contents, and we're going to define what an exponential function is. So first of all, it comes in the form of a times b to the x, where a is not equal to 0. Now a is kind of like the leading coefficient, as we've seen in other families. A wouldn't equal 0 because it would make the whole exponential portion of that equal 0. The base of our exponent is always going to be a positive number. So what if we see negative 2 to the x? Well, this is a little deceitful because there's no parentheses. So we're not really seeing negative 2 to the x. What we are seeing is a negative 1 times 2 to the x. That negative 1 is not present, but we need to just make sure that we're aware that it's there. Okay, a third condition is that the base cannot equal 1. Because if the base equaled 1, then no matter what we put in for x, we'd always wind up with 1. And the shape of this graph would take on the form of a line. And this graph shape definitely does not take on the form of a line. The other definition we need to look at is the word asymptote. We're going to be using this word a lot in this lesson. An asymptote is a line that a curve approaches as the curve heads towards infinity. So what that would look like is this situation where that graph comes down and kind of hovers over that line. That dotted line is the asymptote. Now an asymptote can be a vertical line or a horizontal line. In this case it was a horizontal line. Nonetheless, the two shall never meet. The line and the graph will never intersect. There are a few exceptions to this, but we will not study those cases in this course, so you don't have to worry about it, basically. Alright, so I want you to lift this side of your notes, and underneath it I want you to define the parent exponential function. And in this case, a is equal to 1. And then I want you to lift the other side. And if you want to, you can sketch a few of these graphs. An exponential function, basically every graph tells a story. And an exponential function always takes on the following shape. It might be directionally different, but this is the general shape of it. There will be no extra hills or valleys. It basically is a graph that approaches the asymptote, as we see in this situation. That asymptote can float around. So here's another situation. And there's another one. And so the graph and asymptote don't touch, as we've mentioned before, ever. Here's a graph of growth. You notice that it actually starts from the left and rises to the right. The domain of this graph is all real numbers, which means that I can put any x value in, any number in for x without any restrictions. The range will always be positive numbers. You'll notice that this graph never dips below the x-axis, which indicates that the y values are positive. A graph of decay actually starts up from the left and falls to the right. These are both exponential functions, by the way, and their domain and range are the same. It's not contingent upon direction. Alright, so I want you to lift the growth side of your lesson. And a function of the form f of x equals a times b to the x, with a being a positive number and b greater than 1, is an exponential growth function. So in other words, think taking off, like an airplane takes off. Here are some examples. Y equals 2 to the x. Notice it meets the condition. A is positive. The base b, 2, is greater than 1. In this next example, we do see the presence of the number 4, which is the a value. Please keep in mind that we do not and cannot multiply 4 times 2 due to violation of order of operations if we did. The order of operations says you must do the exponents first, and since we can't take 2 to the x, that means the order of operations comes to a stop. So that will not equal 8 to the x. Here's another example of growth. We have a fraction, but it is greater than 1. And here's another example of growth. We're not focusing in on the a value, the 1/5. We're actually focusing in on the base, which is 10. And if that number happens to be greater than 1, then it's going to be a graph of growth, as you can see in this diagram. Okay, so now what we're going to do is take a look at a graph of decay. A function of the form f of x equals a times b to the x with a greater than 0. And the base falls between 0 and 1. In other words, it's a fraction that lives in between the boundaries of 0 and 1. This is going to be a graph of exponential decay. Alright, and so what you need to think is landing. So here are some examples. Again, that base is 1/2. Base here is 1/3. We're going to totally ignore the 3. That's the value of a. And that doesn't determine whether a graph is growing or decaying. In this case, the base is 0.25. So these are all graphs of decay. So here are a few examples that we need to look at. Determine if the equation represents growth, decay, or neither. Okay, so the first example is 3 to the x. So what we want to inspect is the base. The base is 3. 3 is bigger than 1, and so it is a graph of growth. In this example, again, we're going to focus in on the base, which is still 3. Totally ignore that 1/2. That's the value of a. That has another effect on the graph, but it doesn't affect whether it's growing or if it's a graph of decay. So it's also growth. In this next example, if we inspect this, we see that the variable now is the base, and this makes it a polynomial function. So this is not growth or decay. Here is a graph of decay because the base 3/4 occupies territory between 0 and 1. And this one also is a graph of decay for the same reasons. We're going to totally disregard the 5. Again, the value of 5 is the value of a. And what determines growth or decay is the value of b, which in this case is 0.2. Alright, so we have a -4 wrapped up in parentheses. Keep in mind that by definition, the base has to be a positive number. So this is going to be neither. Alright, so that, let's see if there's any, oh, there's one more. Alright, here's another example. And this time we have kind of a little equation in the exponent. But we still have the variable x, and 7 is the base. So it's okay for us to have a little equation in the exponent as long as the variable is just a single x. We don't want x squared or x cubed or anything like that. So this will be a graph of growth due to the fact that 7 is a number bigger than 1. Alright, so that concludes this lesson, and hopefully you now know what the general shape of an exponential function looks like and whether or not it is increasing or decreasing. Alright, we'll see you next time.